start on unsupervised machine learning. But in our our early introduction, we understand what unsupervised machine learning is. Ideally speaking, is the models that learn pattern from unlabeled data. Okay. So with me here, I have an image. I have an image. So under unsupervised machine learning algorithm, we want to talk about two things: clustering techniques and dimensionality reduction, or what's called PCA. PCA means principal component analysis. Okay. Now, the goal of unsupervised machine learning is to discover hidden structures or groupings. Okay, if you compare unsupervised machine learning and supervised machine learning, in unsupervised machine learning, in the supervised machine learning, we're using labeled data. Okay, you're able to see what's the input and output mappings. Unlike in unsupervised machine learning, we don't have any output, so there's no explicit output mapping. We just have a group of things clustered together, crowded together, sorry, and then we want to find how we're going to derive patterns or structures or groups from this particular group of objects. Think of it this particular way. I'm a business person, okay? I have a variety of customers from all demographics and all age groups. Then I want to classify or I want to cluster my data and to group my data based on maybe let's say people who are of high purchasing, and then again it's who are low purchasing. This first way I can group my data. I can also group my data based on age group, like those who are of age between 25 to 30, and those who are of age 30 to 35, or even those who are the children who are of, young adults from age 18 to 20 or 18 to 25. I want to cluster or I want to group those particular customers of mine based on those particular demographics. And I don't have any label. I don't have something like, oh, someone who is of age 18 to 20, I want to label it as a young adult. Or someone who's spending less than 10,000 shillings, that's a low purchasing person. And that person who's spending more than 10,000 per month or per week, based on what I want to investigate, is a high purchasing person. I don't have any that kind of label. I don't have that any kind of label. So what I is speaking, we have hidden patterns or hidden groupings in my entire data. So supervised machine learning is the model that learns pattern from unlabeled data where you have no explicit output. Okay? Hope you're able to understand that, Mr. Dennis. You can mute now. We proceed. Now, with me here, having groups of, let's say, blocks. I have those that are circular. Let's take this particular scenario. I have circular blocks, I have triangular blocks, I have rectangular blocks. But we have no label. We have not labeled this, no, because it's a perfect, it's having smooth edges. This is a circular block. No, there's no edges. Now, if I write a PCA or a principal component analysis, that algorithm is able to, even if I write the k-means, that particular algorithm, k-means clustering, will be able to group my blocks here based on their shapes. Okay, I can decide to group them based on shape or based on color. Why? Despite them having different shapes, I'm also having different colors. I can say, okay, this time around, let me group my, for example, in my first way here, I'm going to take everything. I'm going to compare everything, every shape with the same color, and group them together. Despite being triangular, rectangular, circular, I don't care. I want to group them based on color. And I think you're able to see that, Mr. Dennis, right over here. Okay, now In the donor wing, I'm going to group them based on shape. I don't want to care about the color, whether it's orange, whether it's pink, whether it's gray. No, just group my algorithm. I want to tell it to group for me my data. Okay, I'm going to cluster my data based on shapes. So in the first scenario here, blocks are arranged based on color. The second one, blocks are arranged based on shape. This particular image is derived from Ultrasoft. If you go to the website, you'll find this particular image over there. So that's what we are going to do. Now, we're going to use a new data set to demonstrate the k-means clustering and the dimensionality reduction, or what they call it PCA. PCA means principal component analysis. We'll see that in a few minutes. In a few days, how it being implemented in real life data. Now, I'm not going to use my weed seed data to do my particular unsupervised machine learning techniques. Now, let me share you this particular link. You download that data with you, because is what we'll be using. So check in the chat section and see if you can download that data, Mr. Dennis. So we're going to use the data set for wheat seeds. Okay. So let me take you through the data and set information. The examined group comprised kernels belong to three different varieties of wheat. Three different varieties of wheat. So this is what we want to cluster, by the way. Those that are depending on Karma, those that are in the Rosa variety, or those that are in the Canadian variety. We have 70 elements each. Okay, that means they have 70 entries, randomly selected from the experiment. High quality visualization of the internal kernel structure was detected using a soft X-ray techniques. Now, under each of this particular day, how are we going to be able to define whether this is a Karma variety, Rosa variety, Canada variety? Is because there was that soft X-ray that was passed through all of them. Okay, that internal to examine the internal kernel structure of each and every variety, and that one will, ideally speaking, that will form our column names or our features. Now, it is non-destructive and considerably cheaper than other than more sophisticated imaging techniques like scanning microscopy or laser technology. The images were recorded on 13 by 18 centimeter X-ray KODAK plates. Then studies were conducted using combined harvesting wheat grain originating from experimental fields that explored all the Institute of Agrophysics of the Polish Academy of Science in Lublin. So that's where then the experiment was done. Poland, Polish Academy of Sciences in Lublin. You have a paper for that. You have to acknowledge the paper there where it was generated or where the experiment was done. Now, the title of the paper is Complete Gradient Clustering Algorithm for Feature Analysis of X-ray Images. To keep it simple, we have the wheat varieties. Then the wheat varieties were investigating using the internal kernel structure. Okay, so through the internal kernel structure, we're able to come up with the particular features or column. We want to see that when we run the code, we will be able to see the columns, like we have the area size, the parameter size, the compactness of the internal structure, the length of the variety, the width of the variety, the asymmetry, okay, the groove. All that will be able us to identify whether it's on variety, karma rose, karma, Rosa or Canadian. So using all those features, my k-means algorithm will be able to cluster for me these three varieties. Just the same as what we saw right over here. We have three particular colors and then we also have three particular shapes. My algorithm is able to cluster this based on either color or shape, based on what I'll define in my algorithm. Now, we want to write our algorithm starting with the k-means. We want to start with our k-means. So this is the cycle. Remember the cycle. We're going to import the necessary libraries. We're going to read our data. We want to do exploratory data analysis. Then we want to move to feature engineering. Okay, we're going to come up with new features, including the column for the class. We want to come up with that. And then we want to train our model. We want to train our model. Then get the evaluation. You can see the evaluation report by check the accuracy. You can check the classification report. You can even we shall also able to visualize how our model is performing. Now, if we move to deep learning in the next few days, we want to see what are the other aspects like checking. We can specify the number of epochs. We are able to even optimize our algorithm using the Adams optimizer or hyperparameter tuning. We'll be able to see that in the coming section. Now, for now, we want to start working with the scenes data itself. We want to start clustering using k-means cluster algorithm to come up with the to cluster the three with classes. So that's it. Before I move to that, I want to show you the mathematical intuition behind k-means. How does k-means cluster work? How does k-means algorithm work? That's the question. Okay, before we define that, let's see what you have in our data. I'm going to upload my seeds data to my Google Colab first. Datasets. Okay. Seeds data. You can also upload that as well in your Google Colab. Seeds dataset. I hope you can see my screen right over here. Have you managed to upload your data which you downloaded? That's good. So let's proceed. Our first thing that we want to do, we want to import all the necessary libraries. So we want to write import all libraries. So that's our first step. Let me close that and have a bigger environment. So the first obvious one is pandas for reading our data. So import pandas as PD, then import numpy as np. We want to import the visualization library. This we want to import um, matplot lib.pyplot as lt. Then I'm going to import cbon itself as sns. So I've imported all the library required for data loading and numerical computation together with the visualization. So I want to import the libraries for my k-means. I'm going to write import. Okay. I'm going to import from sklan as well. From sklan dot. This time we're going to use a cluster algorithm. Cluster. We're going to import k-means. K should be capital, M capital, the rest is lowercase. So it's from sklan dot cluster. We're going to import k-means. That's our algorithm, the k-means algorithm we're going to use. Now, for our model or for our preprocessing, we want to import the preprocessing library, the standard scale. I'm going to say again from sklan dot preprocessing. Don't worry, I'll share this particular code with you. We just have to copy paste. Just monitor what I'm saying and understand. Then I'll be able to share this with you this particular section. Of course, importing them is not important as knowing how to use them. Then we want to check on we want to import the evaluation for model evaluation. So again from sklan dot our metrics. Now for unsupervised machine learning algorithm, we normally use the Celohit score. The others are using accuracy score and the classification reports. For us here, we want to use the Celohit score. Import Celohit score, and you can see suggested over here. So let's click on that. Again, because I want to use the tool, let me also import the PCA from sklan dot. Again, you're using the PCA. This is decomposition. We call this decomposition. We want to import PCA. Why decomposition? We want to do what's called dimensionality reduction. We see how that happen. Yeah. So Kachak was saying print if you have no error, we shall print all libraries imported successfully. So if I run that, boom, I have all my libraries successfully imported. So that's the first step. I promise you with this particular line of code, let me give you in the chat section, you copy paste so that we move together. That's very obvious. Once that is done, let's move to the next thing. The second step is loading our dataset. I'm going to write here load dataset. This is obvious number 2. Load dataset. Now, what's the process for us to load the dataset? I want to say our data frame, I want to say is equal to PD dot read. We're reading our text file, by the way. Dot read CSV. Then inside I want to pass the path for our data. Copy path, put it here. Now, because we're working with a text file, we want to include a number of parameters. We're not going to leave it at this particular point. We have to include a number of parameters. Suppose we're reading a CSV, this is okay. But since we're using a text file we don't have any commas separating anything. We don't have any split. Just a text file. And like it says with us comma separated values, we have the commas separation. So we have to specify two things. We want to define the column names that we have. Say name or the columns names is equal to the columns. And then we want to specify the separation. Separation, we want to separate them under read function. We want to specify them using what's called a split for S. So S, just take a note, read full bracket S plus to that bracket. Then if we do df dot head, still we won't have that particular code executed. Why? We haven't specified the column itself. So when we open our text file, when you open your text file on the other side, if we see data set, we are able to see the columns there. Let me show you that by example. So I want to specify my column under a list. So let me see what I have in my data first for me to understand what my column values are. Let me open my sys data using a notepad. Now, from here we see that we don't have any column label, but we are given the data dictionary. We have the data dictionary, what each and every column here in my text file correspond to. So we have how many columns? 1, 2, 3, 4, 5, 6, 7. And if the eighth one, that will help us in the classification. I think you can open that in your machine. You will be able to locate that with you. Now, my first column, we have what's called the area. The first thing correspond to area. Okay, all those information we find from the dictionary here. We get the data dictionary. Like, let me show you here. Can you see my screen, Mr. Dennis? Right over here. Yeah. So, in my raw text data, hatujapewa any column name. But with me here, I'm able to specify the column what it corresponds to using my data dictionary. Like the first one there is area. If you're able to open that text file, the first column corresponds to area. The second one is the parameter of your seed. You know, seed, the small, tiny object. So the area of that seed, the parameter of that seed, all these parameters will enable us to classify whether it falls in the Karma category, the Rosa category, or the Canadian variety. We shall use all these features to classify, to cluster my wheat seeds. The next feature there, or the next column, is the compactness. The compactness is given by formula there. Compactness is 4 times pi raised by okay, all times area divided by perimeter squared. That's how they're able to come up with the compactness, the formula. Then the length of the kernel, that's very obvious, in centimeters. The width of the kernel in centimeters are symmetry coefficient. What is symmetry of my seeds? Then the next thing is length of kernel group. That's what I have in my text data over there. Now, let's use that in our algorithm. The first one is area. First column is area. Second one is perimeter. I have to specify it correctly. Perimeter. I think that's what I have. Yeah, that's perimeter. Let me copy this. Perimeter lowercase. Uh-huh. I have the next thing here. Sorry, I have to delete this. Yeah. Good. My next column is the length. Let's do the compactness first. Compactness. Then we have the length. Then we have the width. Length, width, asymmetry. So let me specify that. The length, width, symmetry. Then we have the groove. Then we have the class. So class is our new column that will enable us to understand or classify them in the three classes. Now, in simple terms, what have I done? What have I done? I'm having a raw text file without the columns itself. I have to specify the columns for my data. I'm going to give them the column. The first column will correspond to the area. Second one is the perimeter. Third is the compactness, the length, the width, symmetry, up to the class. So this class value is still empty to enable us to classify my species. So let me run this if my data will be loaded successfully. Let me see what I'm having. Good. This is what I have. Let me view the first 20. Okay. Let me view even the first uh, 6 is too much. Let's say 50. Because it's a small data, it will run very fast. Okay. Let me view the last 5 rows by saying data frame dot tail. Yeah. So for me, you're able to see a number of classes like 3, 1 there. Okay, let me see more classes by defining more records like let me say 80. If I'll be able to see that those classes. Yeah. So you see I'm having 1, 2, and 3. It means I'm having three classes. The first class which I don't know, maybe it's Rosa, maybe it's Canadian, I don't know. It's labeled by 1. The second class is labeled by 2. The last class is labeled by 3. So in my class column here, I am having 1. Then I'm having the area in centimeters squared. I'm having perimeter in centimeters, compactness there, length in centimeters, width as well. All these particular features has been given in my dataset itself. So separation here, R means while reading, I'm going to separate this with any split, any given value, any given space. I'm going to split my data in that order. If you ignore this, you want to have your data run successfully. Remember the plus. If you don't include the plus, you will find an error. That will run, but you'll find a small error. Okay? You're being stored express fields with line, so error could possibly be due to quotes being ignored when the multi-character delimiter is used. So Okay, now the fine details. Let's just include the plus sign here and run our data. Mm. Okay, at this particular moment, we're able to read our data and see whatever we have in that. So let me share this code with you as well. You'll be able to review that later. Okay. Do you have any question at that point, Mr. Dennis? Do you have any question? Okay. I'm really emphasizing on this concept so that you understand them in one is, and we proceed to the next. Okay, the next thing that is obvious is data preparation. Data preparation. That's number three. Okay, by running the code, are you able to see the data loaded? All right, let's move to the next. Okay, thanks so much. Let's move to the next thing, data preparation. You can check the information that we have in our data.info. Though these are just revision, I'll move so fast. I'm seeing whether you have the data type there, the columns that we're having there, and if there's any missing value or non-value, will be shown. So in our data, I'm having 210 records. 210 records. Or we can check for even missing values. But before that, let's check for the descriptive statistics. I'm going to say data.describe. That will show me the descriptive statistics, the count, the mean, the standard deviation, the minimum, up to the maximum for each and every column. Let's check for if there's null, if there's missing value, like say df dot is null dot sum for each column dot is null, then outside here dot sum. Okay, this is so fantastic. We don't have any missing value here. We don't have any missing value. Now, the next thing we can do, now since that we don't have any missing value in our column, let's check on our target variable. Now, let me explain to you something here. Let me explain to you something here. Just in a few minutes, let me pick some call. Now, I want to explain to you something. Remember that during unsupervised machine learning, we don't have any labels. Like what I'm having here initially in my data, one possibly correspond to maybe Rosa category or Kama category. Two might maybe correspond to the Canadian category, while three correspond to another variety. Now, because we're using unsupervised machine learning algorithm, we don't want any label. We don't have any class label. Let's see. We can say that if you see any plant with parameter or area 12.19, parameter 13.20, compactness 0.8783, 5.137, width of 2.9861, symmetry of 3.631, group of 4.870, and then let's call it class 3, maybe Canadian. No, we don't want that particular type of aspect. So what are we going to do? What are we going to do? We want to drop this particular uh, column. Now this now what we learned earlier on come in handy. How do you drop a column? How do you drop a column? Do you remember that, Mr. Dennis? How you drop a column? Okay. Now, don't confuse it with the missing values. The missing values use the drop now. But for us, we want to drop a column. How? We're going to say we want to drop a target column. Our target column is the class. Okay. So that's the next thing. Let me write here. Uh, Drop a target column. Now, my target column here, I'm going to give it X to be my remaining data will be data frame, okay, dot drop. I remember the drop function earlier on, okay, dot drop. Then here I'm going to specify my column. My column is for axis. Where is it? Is the my column is the class, the class. I'm going to say here class. That's my column. Then where's my axis? When I say axis is equal to 1, that means what? The rows, the column itself. Hey, very careful. I was checking on that. So axis is equal to 1 means the column, while axis is equal to 0 means the rows. That's great, Mr. Dennis. I see you're attentive. Now, when I write that, let's see what I'm having. X. I'm having my data without the class column. Is that true? So you can see that one over here. Can you see that, Mr. Dennis? Yeah. Now, I've dropped my class axis or my class column for me to be able to implement unsupervised machine learning algorithm. Now, I want to move to what's called the scaling, the feature scaling. Feature scaling. I'm going to explain to you what it means. My next step is feature scaling. All the concepts we learned earlier on, they'll be implemented in this particular section now. Feature scale. Oh, I'm having another call. Just 1 minute. Coming back. We can proceed. I'm done with that call. I want to do what's called feature scaling. So feature scaling is a data preprocessing technique that helps standardize or normalize a range of independent variables. Like for me here, my independent variables that will help me to classify or will help me to cluster my dependent variable class as the area, parameter, compactness, length, width, asymmetry, and group. Those are my independent features or my independent variable. So, feature scaling is one of the data preprocessing techniques or steps that are used to standardize or normalize a range of independent variables, like what I'm having right over here. Okay, so it ensures, why are we scaling? It ensures that all features contribute equally to a model. By doing so, it ensures that all features or all columns contribute equally to a model, preventing variables with a larger numerical range to be given a priority or to dominate the result. Okay, for example, if I look at my data here, area, area here seems to have more or higher values than the compactness. This one has decimals, while this one has whole numbers above 10. So when I don't scale my data, my machine learning algorithm will force itself such that the column area will dominate my result, which is not okay. So standard scaling or feature scaling will ensure that all the columns that I'm having here contribute equally to my models for k-means and PCA. This will help prevent variables with larger ranges or larger values from disproportionately dominating my result. And that's why I want to do that. So the next thing here is the scaling. How are we going to use the scaling? I imported a function here. Oh no, I imported a variable here called standard scaler. From sklearn.preprocessing import standard scaler. There's no harm of importing it just for you to see it. I'm going to define my scalar, just a variable scalar. I'm going to say is equal to standard scalar. Just get it right. So you know why you're doing that. Then I would say x scaled my data itself. X scaled. I'm going to call the scalar itself here. Scale dot. Now let me fit my data. Fit transform. Where's my data? X over there. So let me copy that and put it here. So x scaled, my data that has been scaled is going to be scalar. Where's my scalar? It corresponds to the standard scalar itself for standardization. So feature standardization or feature scaling, you know why? It will enable to bring that smoothness or that fairness in my data. Not that all my data with higher values or higher ranges to dominate my model or my results. So that's what I want to do. Let me run that and see what we have. That has been perfectly done. My next thing onto what's called EDA or exploratory data analysis. Exploratory data analysis. I'm taking you through the entire machine learning model life cycle. Entire machine learning model life cycle. Nothing will be left behind. So EDA. So EDA you can use to view your data, just another view. So let's do only one. You can build a correlation heat map to see how my data has been arranged, or the relationship, or the correlation in my data. You remember this earlier on when we did our visualization. So I'm going to say SNS, you know that SNS is from Seaborn dot heatmap. Then under heat map, I'm going to do what's called a correlation. So data frame, I'm going to correlate that, do correlation, then the annotation, I'm going to make it to be true. Okay. So let's say plt dot title. Let me give the title like the feature correlation. Features correlation. Then I would say let me plot my title. Okay. This should be a closing quote. Good. Plt dot show. Otherwise, you can give it anything you want. The axis, all that you can define. Problem here, I thought, correlation. There's a problem there. So this is my correlation analysis of my entire features. The area, the parameter, the compactness, the length, all the way to class. Okay? So you can see here, area versus area. We have a perfect correlation. Parameter against area, you have 0.99 correlation. That's a positive correlation. Even in fact, it's a strong positive correlation. Compactness versus area, you have 0.61. This is a weak positive correlation. Okay, you understand that a strong positive correlation starts from 0.7 all the way to 1, while a weak positive is from 0 to 0.69. I hope you remember the correlation analysis that we did earlier on. So just connect the dots, you will see that as well. So I've done a simple EDA for my data. Okay, you can do even a pair plot, you can do a histogram, you can do anything that you want. So let's start working on our k-means. So let me show you what k-means is, what is the mathematical intuition, and how does it operate. Okay, let me show you that right over here in a few minutes. Yeah, yeah. I hope you can see my screen today. Just give me a thumbs up if you can see my screen. All right. Anyway, don't worry. The class is being recorded. I'll show you the video after a while. Let me enlarge this. Now, K-means clustering is unsupervised machine learning algorithm used to group data into K clusters based on one thing, similarity. Based on similarity. Like for our example, we're going to group our data based on those particular features, the length, the parameter, the compactness, the asymmetry, all that will enable us to group our width seeds on the three classes. Do you remember the three classes? The Rosa, okay, the Canadian. Which one was the last one? The Rosa, the Canadian, and the Kama. See, remember the three varieties over here: the Kama, the Rosa, and the Canadian. All the features will enable us to group that as well. So let's go back to our data, our explanation here. For example, I can have a figure here, by the way. Okay, figure one here. Before applying K-means clustering, this is what I have. But after applying K-means clustering, I'm having it clustered into three. I'm having cluster one with the red denotation. I'm having cluster two, the green one, and cluster three, the blue one. I think you're able to see that, Mr. Dennis. Can you see that over there by thumbs up? Yeah. I'm having my figure before clustering, applying the K-means clustering. After doing that, it has been clustered into three of them. Cluster one by red, cluster two. Is it green? Is it jungle something? Huh? A green like it's a green like class. Then I'm having the class three, the blue like thing. Now, when is came in use? Let's check when is it being used for customer segmentation. Like you can group your customers based on purchasing habits or based on the demographic situation, like those who are in the urban, those who are in the rural. Okay. The second thing you can do is in market basket analysis, or you can do it in image compression. The fourth way you can use it in anomaly detection or finding errors. We want to see that in a few minutes. For us, we want those called segmentation or grouping. Our three particular seed classes. That's what we're going to use. There's that particular mathematical explanation of how it works. We want to initialize, we want to assign a data point, we want to update, I want to repeat all the steps two to four. And by the way, I want to share with you this particular section. We'll understand that into details. So we're going to use the loss function as well to find the most optimum uh, results. So let's proceed. After this, we want to write our k-means cluster algorithm. I see we only have 3 minutes. Let me define something here. I want to find first thing I want to define the elbow method or find the optimum k. Remember we said that you have to define the k. You have to initialize the k value. Here, our first step is to initialize or randomly select a k point, k value. K can be something like 3, 2, 1, something of that sort. It's like the pivot point, the pivoting. Like if I look at my image here, I can decide to put a K somewhere in the middle. Then I'm going to move left, right, every corner and see if I'm having any similarity. I'm going to classify that into one particular category. And though that's what we're going to do. So let me do one more thing here before we proceed. I'm going to call what's called the inertia. I'm going to give it a blank space. Then we'll say for K, it's a variable for K in range. Let's say 1 to 10. That's what we'll select any optimum k value. Okay, let's say from 1 to 10, you can put it 1 to 20, any value you want. I'm going to call the k means is equal to k means itself. K means, okay. Then inside here, I'm going to say n clusters to be k. Though we don't know this particular value of k. It's what we're finding out. N clusters to be k. I don't know whether they're 3 or 4 or 5. I don't know. Because I'm not told now we're having 3 or 4 labels. I want to find out. Then I'm going to say random seed. No, why random state, sorry. Random state is equal to 42. Right now you understand what random state mean, and I explained to you that as well. This will help to reshuffle the data. Then let me call this particular k-means. Let me k-means. I don't know why it can't copy paste. Yeah, k-means is going to be fit. K-means dot fit, where are we fitting our model the X scale data, our scale data over here. You've scaled our data to avoid the idea of the biasness or the priority given to those columns with the higher values. That's my new data. It's been stored in the X scale. Then let me call my inertia here. I'm going to populate my data. I'm going to find my k. I will say inertia dot append. I hope now you understand the append function. We discussed that earlier on. K means this particular k means over here. K means dot inertia. Ah. So this inertia is a function, but the inertia here is where we're going to store the k value. Okay. Now, what are we doing? We're trying to find the elbow, like finding the optimum k. Let me give that as a title. Finding the optimal k value. Because you don't know using what's called the elbow method. Using the elbow method. Let me show plot. I can even plot the elbow. You see how it appears. Okay, let me plot the elbow. You see how it appears, how it moves. Let me plot what's here. I'm going to say plt dot plot. From the range 1 to 10. Okay, let's say range. Where's my range 1 to 10? Okay, then comma my inertia itself, where my data is being populated inside here. That's where my data is being populated. Inertia. Let me give it the markers. Okay, this is optional. You can give it the markers. How do you want it to be displayed? What are the points? Just to mark that, I'm going to use something like, I can use a star X or use something like zeros. So let me use zeros or O for that matter. Then I can give it a title. Okay, you can give it the Y label, the X label, all that is we were able to do that earlier on. So let me run this code entirely. Yeah, so this is what we have. This is what we have. Let me change the markers. I don't know if it will be separated. I don't know. Yeah, so our markers is starting here, star, 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 star. Okay. Hope you're able to see that, Mr. Dennis. Let me change it to maybe plus, plus, plus to give it as the markers. I'm having it here 2, 3, 4, 5. So this is the elbow method that we have used. You see, it looks like an elbow, perfect elbow. So by this, we'll be able to find the optimum value of k automatically. Okay, I don't know whether we can proceed. I'm seeing we are over time. Let me do one last thing before we stop it. So k means what I defined earlier on is equal to k means itself. K means algorithm. Okay. Then n clusters. Let's just choose any pivot point. N pivot point. N cluster to be, let's say, three. As you don't know, let's just put that particular point. Though this particular value will change based on the optimal point for my elbow method. Random state is equal to 42. That's obvious. Then let me select my labels is equal to k means, okay, dot fit predict. Then instead here I'm going to specify my data. Where is my data? The x scale itself. I know you're worried. Why are you doing all this? All that should make sense in a few minutes. So you can do a simple thing. We can cluster. We can now print out our k-means classes. So let's do one last thing before we move. We stop. So what I'm going to do is k-means classes. Before doing the algorithm running it, I want to print my original classes. How it looks like to my data visually. K-means classes SNS dot plot. Let's use scatter plot. Dot scatter plot. Scatter plot. X value, let's use compactness. Let's use compactness. Okay. Then the Y value, let's try it again is the asymmetry. Let's use asymmetry. I don't know the spelling. Asymmetry. Double M, I believe. Asymmetry. Then Q is okay. What is the specific way of differentiating the markers? Hue, let me use the cluster. Okay. Then where is my data coming from? I can specify this earlier on, but I can let me just write it here. Uh, my data is from the data frame itself. So this is my original data without doing the using the X scale. So let me plot the title and let me show my data. Let me show my cluster, k-means classes before doing the running through the algorithm. So let me run that and see. Okay, I'm finding an error, compactness. So I knew this could happen. Let me come and copy this. Uh, Place it here. Let me run this and see. Is there any problem again? Cluster. Mhm. Let me see the problem itself. Here. Okay, let me run this one here. Let me run all. Mm, okay, let me ignore this first and see what is the problem. Let me use. Okay, let me try another one here. 1 minute. Yes. But oh, it's the classes. Let's specify the class and see. If you have. Mm-hmm. Okay, now you want to label the colors based on the classes. So we have the class column there. Let me print my data. See what I'm having. Okay, let me do this. X. The data frame itself. Yeah, so I'm having the classes. Okay, basically the hue here, it enables you to have different colors for different unique categories. Like here, the class. Class 1 is denoted by the pinkish color. Class 2 is it the light purple something, while class 3 is the black colors. Class 1, the pink, class 2, purple, class 3 is the dark ones. So I'm able to see my original clusters. This particular line of code gives the same thing. That's what we have. Okay, now let me stop from there anyway. We are going to compare the actual classes against the k-means classes. Are we going to have a difference? We want to check the difference between the actual class and the original classes, or the classes that's to be generated by the k-means algorithm. So next time we want to run the k-means algorithm and check the difference in the classes. So because of time, I see we are uh, over 20 minutes past time. We can just stop from there. We'll proceed tomorrow with a new thing. So that's part one. We shall move to part two. Come tomorrow. I mean, come next week for that matter. We shall see what to do.